All right, welcome to the start of the videos for exam 3. This is section 7.1, and section 7, well, chapter 7 is analytic geometry. And so there's geometry, like if I said this is a circle and just talked about that, that would be geometry. But if I said, no, I want you to graph a circle in a certain location on a grid, then it becomes analytic geometry. For example, x minus 2 squared, y plus 1 squared equals 4 is a circle centered at 2, -1. Would help if you could read my writing. And you should already know how to do that, right? And then slope is 2, or not slope. Radius is 2. And we have not just a circle, but a circle in a certain location. All right, geometry versus analytic geometry. And section 7.1 is an interesting section, in the book. You might think I think all sections are interesting, but no, it's a unique section in that there are no examples and there are no homework exercises in 7.1. It's the only section where the author does that. I'm not sure why it's a section in itself. They could have merged this with another section, but it's almost like an introduction to the chapter rather than an actual section. Usually sections have things you expect in a section, like examples and homework problems. There aren't any. So here it is, our objectives. Know the names of the conics. So the root word for conic is cone. And so these are, know the shapes that involve a cone. Somehow my marker is a little thick. Okay. So here's a cone. By the way, I don't know, this is kind of more fun than, serious science, but I'm going to go ahead and do something here. I'm going to chop this cone right here and just kind of take it out. And if I do that, I'm going to create a very familiar object. A truncated cone. Actually has an interesting name. It's called a frustum, but frustum. The tip is a cone. This part's a cone. That part, frustum. Not that important. But it's a cup. A cup is what you get if you take a cone and get rid of part of it. And I'm just talking about like a solo cup or something. Right? I bring that up because you're very familiar with this. And you might not be so familiar with this whole double cone thing. But there is a connection. And everything the author talks about here, we'll talk about here. Sort of. So they just talk about a right circular cone with 2 napes, or a cup. Cup works just as well, sort of. Conics is an abbreviation for conic sections. So they're like sections of a cone. Well, literally, they are sections of a cone. So we talk about conic sections in this discussion. All right. So the easiest conic section to think about is the circle. Let's get that frustum. And let's say this cup has liquid in it, like soda, and I'm holding the cup perpendicular, like if I took this little piece right here, this plane, I laid it on a plane perpendicularly. All right, so like a table. What do I see when I look inside this cup? You've literally done this every time you've had a drink. You know, if you looked inside, you might see some sodas or you might see some ice cubes or something. But I'm talking about this rim, this shape right here, not the entire surface, but just around here. Well, what you're looking at is a circle, and you know this circle just from your cup intersecting with the soda or whatever it is, your drink. I probably could have drawn that a little better, but all right. An ellipse is when you take that cup and tip it just a little bit. So I already told you what it is. If I tip it, so what I'm doing, here they're tipping the plane that's intersecting the double nap cone. But here I am tipping the cup. Same idea. Relative to each other, I'm tipping it. What am I looking at now? Well, the shape that I'm looking at is an ellipse. And an ellipse is a very specific shape. But it is an ellipse. And by the way, the ellipse is very different than the circle. With a circle, there's only one way to get it. I have to hold the cup perfectly straight. With the ellipse, I can tip it a different amount, several different amounts. It's still an ellipse. If I tip it anywhere from, well, there's a limit. We'll get to another one. But I can tip it quite a bit. Let's get to the next one. See how that one. All right. The parabola, this time, I'm taking my cup with a lid. It only works if it has a lid. And it's fairly full. Yeah, I'm getting a lot of emails, and I didn't turn them off when I started this. Okay, I'll take care of that in a moment. When I started, my cup was red, and my soda was blue. Not all that important, but cups usually are red. But anyhow, all right. So I'm trying to draw what I have here. So basically what's going on here is this little wall right here and this plane are perpendicular. So what I'm doing is I'm laying this, or parallel. So if I lay one edge parallel to the table, and this has a lid, and all of this is the liquid here, right? What am I staring at? Well, it's no longer an ellipse. Remember, an ellipse was where it kind of started closing back on itself. No, this is a parabola. So they're saying the plane or the solo cup is tilted a little farther, so it's parallel to this, what you're looking at. And if you have that, you have a parabola. We're not done. let's say I hold the cup like this. It would be like if I took my two hands and held the cup like in a way where I actually tipped it further than I tipped it for the parabola. There's another thing here that's going to explain these other two napes of the cone, and that is the assumption in algebra and geometry is that lines go on forever. So, and I assume you've heard that. Lines don't just stop. Those are line segments. Lines go on forever. So as soon as I have this cone, I can think of it kind of going on forever. All right. It's filled with, let me draw the other cone over here. My scale's off. My scale's off, so I'm going to do this again here. All right. Cone. I'm really just recreating this, but I want you to picture what I'm doing here. I'm holding a cup between my hands. And if I do that, I get something that kind of looks like the parabola, kind of, but it's different because this is the first time where if I was just talking about a parabola and extended these lines, there's no interaction, there's no intersection. I wouldn't create a second part of the graph. So parabolas just look like this. There's one part to it and we're done. The hyperbola is from lifting this edge up just a little bit or tilting it down just a little bit more. And so it's no longer parallel, but I tilted it enough so that this line actually does rise, and the level, whatever the water level is that I'm thinking of, does this. And so what we get is this figure that I think I've already told you that this is a really bad way to think of a hyperbola because I don't have the asymptotes drawn in, but I get something that's not quite a parabola. I mean, it's a very different shape than a parabola, namely because it has two parts to it. And that's really about it. Now they talk about degenerate conics, where, you know, that would be like if I gave you a circle, x minus 2 squared plus y minus 1 squared equals 0. Well, is that a circle? Or would we say that's just a dot because a radius of 0? So degenerate, a point. We don't really do too much about that. I'm not even sure why the author brought it up at this moment, but that's it. There are no examples. There are no exercises, just these names and kind of knowing the background. And we don't even use the background. We don't really use this. You know what we're doing because you've been, we've previewed a lot of this idea. Sorry, this is going on so far. Okay. We're talking, this is a language. Well, it's a little different, but this is mostly the language of this chapter as well. So this idea of the actual geometry, the underlying geometry, is, I'm just going to call that nice to know. But author likes to do it, and so do I. Touch on the ideas that that generate, or where these ideas grow from. But anyhow, that is section 7.1.